welcome to the week 9 of. Hello and welcome to week 9 of the TA session of Structure Analysis 1 taken by Professor Amit Shah. I am Trisha Chakravarti, one of the course teaching assistants. I am a PhD student at the Indian Institute of Science, Bangalore. As always, I'll start with a recap of the previous weeks. The course is divided into two phases: analysis of determinate structures and analysis of indeterminate structures. The first half, the first 6 weeks, dealt with determinate structures. In week 1, we looked at the basics of structural analysis, like the types of internal forces, the common classification of elements and boundary conditions. Structural in the basics of structural indeterminacy and bending moment and shear force diagrams, how to draw BMD and SFT. In week 2, we moved on to trusses in particular, which is one of the idealized types of elements that only take axial force. They only take force along its length, and they are therefore called two force members. We looked at stability of trusses and how to solve the member forces of a truss using method of sections and method of joints. In week 3, we looked at the other type of response that a structure that is of a structure that we need to study apart from the force response, the displacement response, the displacement of the strain response. For that, we looked at the principle of virtual work, which has been used afterwards in several other weeks as well, because it is a concept that is very widely used in structural analysis. The unit load method to determine displacement in truss, the nodal displacements. In week 4, we looked at the same about beams, the deflection profile of beams. In a truss, we are concerned about the x and y direction displacements at each of the nodes, while in a beam, we are concerned about the deflected shape. Along the length of the beam, we want the deflected length, the deflection at each of the points as x varies from 0 to L. Then there are several methods for that. The elastic curve equation method that deals with the basic governing differential equation of the beam. Then the moment area method and the conjugate beam method. Moment area method and conjugate beam methods are both variations, simplified versions of the elastic curve equation method, and of course they all give the same result, either equal results. In week 6, we looked at a different concept, the influence line diagram, which basically deals with the response of a structure as a load or a set of loads moves across it. We focused on beams, but we can have influence line diagram of trusses and frames as well. But mostly beams is included in this second year course. And as a set of loads moves across the length of the beam, we want to find out the maximum or critical responses. We looked at the Mueller-Breslau principle that gives the ILD qualitatively, and we also looked at how to find it quantitatively, and how to find out the absolute maximum bending moment and shear force under point loads, a series of point loads like the wheels of a car or a truck or something, and uniformly distributed loads greater than or lesser than the span. Then we moved on to phase 2, that is the analysis of indeterminate structures. This basically includes, so far what we have done, we have reviewed the degree of structural indeterminacy of different kinds of three different kind of elements. Beams and trusses we have looked at so far. Introduction to force and displacement methods. Basically, in indeterminate structures, we have more number of unknowns than the number of equations. So we need some additional equations in order to solve the system, and that is where these two methods, these are the two approaches, basically the force approach and the displacement approach, to get those extra equations to solve the system. We looked at the Maxwell-Betty's reciprocal theorem, that is a shortcut to solving some kinds of problems. And began with the force method, the method of consistent deformations. Now in week 7, we saw how that method is applied to beams. In week 8, the previous week, we looked at how it was applied to trusses, and today we are going to look at how it is applied to frames. Frame is basically a structural element that you can call as a combination of a beam and a truss, because a truss element takes only axial force along its length. A beam takes shear force that is transverse or perpendicular to its length, and bending moment. And a frame element takes all three. A frame element has three forces basically: the axial force, shear force, and bending moment. Structural indeterminacy is defined that structures that cannot be analyzed using statics or equations of equilibrium only are called indeterminate structures. As I said, that they need some additional conditions, like for example, they need other material property to be solved. The degree of indeterminacy is the number of unknown reactions minus the number of equations of equilibrium. If it is greater than or equal to 1, the structure is indeterminate, and if it is equal to 1, then sorry, if it is greater yes, if it is equal to 0, that is the number of unknown reactions is equal to the number of equations of equilibrium, it is a determinate structure, a stable structure. And if it is less than 0, that is the number of reactions is less than the number of equations, then it is an unstable structure. And we do not look at unstable structures, we only work with determinate and indeterminate structures, but they have to be stable. The external indeterminacy is the total number of independent support reactions minus the total number of available equations of static equilibrium. This concept remains the same whether it is a beam or a truss or a frame. The concept of we know that the independent support reactions, we know that the kind of support, that if there is a fixed support, it offers three kinds of constraint, three reactions: in the x direction, in the y direction, and a moment. Hinge support offers two reactions. So we, from the kind of support, we know we can identify the number of support reactions each support will provide. We can add them up, and the total number of available equations of static equilibrium is also always constant. In a 2D plane, it is always 3, and in a 3D space, it is 6. And internal indeterminacy is total number of internal reactions minus available equations of equilibrium. This is a little harder to perceive. So we generally, the approach we take is, we have formula for external indeterminacy, we have formula for degree of total structural indeterminacy, and the internal indeterminacy we can find by subtracting. Like, degree of structural indeterminacy is the sum of external and internal indeterminacy. So if we know any two of these, we can find out the third one. These are some examples that we looked at the previous week as well. Yes. So the first is a beam under uniformly distributed loading. This is a fixed support. It provides us three reaction forces, and since it's a 2D structure, it has three equations of equilibrium. So the degree of static indeterminacy is 0. It has no it is a determinate structure. We can easily solve it. We can solve these forces simply by the equations of equilibrium. This is a propped cantilever where there is a fixed support at one end and a roller support that only gives a reaction perpendicular to the plane, that is RC. So there are four support reactions unknown, three at this A point and one at this C point, and we have three equations. So this is indeterminate, 1 degree indeterminate. This is a frame structure with fixed supports at both A and D. So we have 3 plus 3, 6 unknowns and 3 equations. In frame, we have 3 equations. Whether it is a frame or a beam or a truss, in 2D plane, we have 3 equations of equilibrium. So this, we have 6 minus 3. So the degree of indeterminacy, total degree of indeterminacy is 3. And this has two hinge supports. Hinge supports give us two reactions each, in the x direction, y direction. Here also in the x direction and y direction. So we have four unknown forces and three equations. So this is indeterminate to 1 degree. Today, since we are looking at frames, these are the formula that we need to remember for frames. For 2D rigid, we are only looking at rigid frames. Rigid means that there can be no relative movement. Like, if there are two members of a frame like this, they cannot have they cannot rotate or with respect to each other. That if there is a 90-degree angle between two members, a 90-degree angle has to be preserved. Or if there is a 60-degree angle, the 60-degree angle also has to be preserved. So that is what is meant by rigid frames, and we are only looking at rigid frames right now. And so 2D rigid frames, the degree of total indeterminacy is 3m plus re minus 3j, where m is the total number of members. Why do we multiply it with 3? It is because each member has 3 unknowns. Along each member, we have an axial force, a bending moment, and a shear force. So we have 3 unknowns, plus re is the number of external reactions. For example, in this frame, we have 6 re. 6 re is equal to 6, and minus 3j is the number of j is the number of joints. In this frame, for example, we have 4 joints, 1, 2, 3, and 4, and at each joint we can have 3 equations. Again 3, because you have a force in x direction, force in y direction, and a moment. In truss, remember that in trusses that we studied the last class, this was 2j, because in a truss bending moment is not really in question. So in at every node of a truss we only have two equations. The sigma fx equal to 0 and sigma fy equal to 0. Moment is not in question. But in frame, since a frame member can also undergo bending moment, we can conserve moment at each joint. So the degree of total indeterminacy is this when all joints are rigid. And this is when some joints are hybrid, we'll look at this later. And for 3D rigid frames, the 3's becomes 6, because in a 3D space, if you look at axial force, shear force and bending moment, and there is another extra moment called torsional moment as well. So if a frame element is oriented in a 3D space, there will be three translational forces. One is the axial force along the length of the frame, then there is one shear force in the x direction and one shear force in the z direction, or not just, I mean, if you assume that the axis of the frame is x, then you can find out at least two other axes perpendicular to each other, y and z, that have independent shear forces. Like, of course, you cannot say it has some shear force component along every axis perpendicular to its own axis, but we can only say that only two of them are independent along two mutually perpendicular directions. So if a frame element is oriented around the x direction, you can find a y and a z axis. So we have axial force along x, you have shear force along y, and shear force along z. There are three unknowns, and the three forces, and the moments are, you have a bending moment along about x, you have a bending moment about y, a bending moment about z, and the moment about x. A moment of a frame element about its own axis is what is called torsion. Torsion is basically that the moment that you apply along the along the member length. So there are three forces: one axial, two shear, and three moments: two bending and one torsion. So there are six m unknowns. For each member there are six unknowns. So total internal unknowns are 6m, and the total external unknown is re. Of course, if you are looking at a 3D space, then if you have a fixed support, you have to take re as 6 for that fixed support, because in a 3D space a fixed support gives six constants, while in a 2D plane it gives only three constants. And at every joint, similarly, you have six forces each. At every joint, you have sigma fx equal to 0, sigma fy equal to 0, sigma fz equal to 0, and similarly sigma mx, sigma my, and sigma mz are all 0. So you have 6j equations, and this is the degree of static indeterminacy for a 3D rigid frame. This the degree of static indeterminacy for this rigid frame. See, this RR is basically this, some joints are hybrid. This RR, for one of the examples of a hybrid joint is an internal hinge. In a 2D plane, this internal hinge actually gives you one release, one additional equation. We have, when we studied internal hinge, I mean, when we solve problems of beams in with internal hinge, we know that it gives you one additional equation. So that is why it is subtracted. Basically, this plus part is the number of unknowns and the minus part is the number of equations. So in this RR we get, there is an additional equation, so we subtract it. And in 3D space, an internal hinge gives us three equations, so RR will be 3 in a 3D space. Here there are 5 members at every support and every hinge. Everything you have to consider as joints, and there can be only one member between two joints. For example, like, don't call this one member, this is two members, since there is a support here. So there are total 5 members: 1, 2, 3, 4, and 5. And there are six joints: 1, 2, 3, 4, 5, 6. The total number of external reactions, let's see, this is a fixed support, these three are all fixed supports, so we have three unknowns each from that. So 3 into 3 is 9, and this is a roller support that gives a perpendicular reaction in this direction. So RE is 10, and RR is the internal hinge, the release due to internal hinge. So we have one extra equation, so we subtract a 1. So anyway, degree of this is the formula that we studied. Degree of static indeterminacy is 3 into 5 plus 10 minus 3 into 6 minus 1, that is 6. And degree of external indeterminacy is always the total number of external support unknowns minus the total number of equation equilibriums. So this DSC will be 10 minus 3, so that is 7. So 10 is the total number of support reactions, and 3 is the number of equation of equilibrium. So 7 is degree of degree of external indeterminacy. Total degree of indeterminacy is 6. So degree of internal indeterminacy is minus 1 here. For this 2D frame, again we will follow the same approach. Let's count the number of members: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. This is also a joint. I mean, for this diagonal we have two elements, and for this diagonal, since there is an internal hinge and a joint here, we have three. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 members. The number of joints is 1, 2, 3, 4, 5, 6, 7, and 8. This internal hinge is also a joint, as I said. And the total number of external reactions is one hinge and one roller. So there are three external support reactions, here in the x direction, in the y direction, and here in the y direction. So immediately you can say that the degree of external indeterminacy is 0. I mean, seeing this structure, whatever the internal structure may be, you can find out the support reactions because you have three equations and three unknowns. And so using this formula 3m, and there is one internal hinge, so there is one rr is 1. So ds, the total degree of indeterminacy, is 3 into 11 plus 3 minus 3 into 8 minus 1, that is 11. And this entire 11 degree of indeterminacy is internal, because externally the structure is determinate. That is why dsc is 3 minus 3 0, and dsi is 11 minus 0, that is 11. This is a 3D frame, 3D hybrid frame, and here the number of members is 1, 2, 3, 4, 5, 6, 7, 8, 9, and the number of joints are 1, 2, 3, 4, 5, 6, 7, 8, and 9 again. And the number of external support reactions, let's count. We have two fixed supports and two hinge supports. Now fixed supports and hinge supports obviously behave differently in the 3D space as compared to the 2D plane. So each fixed support gives us 6 reaction. Fixed support, this 6 plus 6, and these two give 3 each in 3 translational directions: x direction, y direction, z direction. So the number of external support reactions is 6 plus 6 plus 3 plus 3, that is 18. And the total number of basically the total reactions released when two members meet at a point. This is the formula that you can remember. RR in 3D plane, if 3D space, is 3 into m dash minus 1. Basically, m dash is the number of members that meet at the internal hinge. So far, the questions we have seen, only two members meet at the internal hinge. In that case, in a 2D plane, you have one release, and in a 3D space, you have three releases. But if three members met at a hinge, then the number of releases will be more. Anyway, here we have three releases for an internal hinge where two members meet in a 3D space. There are three releases. So this formula is the total degree of total degree of indeterminacy is 6 into 9 plus 18 minus 6 into 9 minus 3, that is 15. And the total degree of external indeterminacy is number of support reactions, 18 minus 6, because here we have 6 total equilibrium equations. So the degree of external indeterminacy is 12, and 3 is therefore the degree of internal indeterminacy, 15 minus 12. This is an example where more than two members meet at an internal hinge. This is in a 2D plane. So basically, if the number of members meeting at an internal hinge is m dash, then you have m dash minus 1 releases. So in this, for 2D plane, so here the two members met, here two members met, so we had one release each. And here, since for each of the this internal hinge and this internal hinge, three members meet here, right? 1, 2, and 3. So there are two releases here and two releases here. So let us count the number of members: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And the number of external reactions, we have four fixed supports, and in the 2D plane there are three unknowns each, so 4 into 3 is 12. So the number of external reactions is 12, and immediately we know the number of the degree of external indeterminacy, because we have three equations of equilibrium and 12 unknowns, so 9 is the degree of external indeterminacy. And the number of joints is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Sorry, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the number of releases is for in each internal hinge, since three members meet at this hinge, we have two releases, and at this hinge also we have two releases. So RR total is 4. So this in this formula, the degree of static indeterminacy is 3 into 12 plus 12 minus 3 into 10 minus 4, that is 14. And the degree of external indeterminacy was 9. So the degree of internal indeterminacy is 14 minus 9, that is 5. This is here again, see here two members meet, right? So at this internal hinge, if two members meet, then we will have one release. And the total number of members is 1 2 3 4 5 6 7 8 9 10 11 12. The number of joints is 1 2 3 4 5 6 7 8 9 10 11 12. And the number of support reactions, we have four fixed supports like the previous question. So 4 into 3 is 12. So the number of unknowns is also 12, external unknowns. And the external number of equations is 3. So degree of static indeterminacy, degree of external indeterminacy is 9. And this in this formula, we have here we have rr equal to 1 because only two members meet here. So 3 into 12 plus 12 into my 3 into 12 plus 12 minus 3 into 12 minus 1, that is 11. And the degree of external indeterminacy itself was 9. So the degree of internal indeterminacy is 11 minus 9, that is 2. This is another frame here. Basically, this has no internal hinge, so there are no releases. RR will be 0. The number of external reactions is 1. There's a fixed support. This has 3 reactions. This is a hinge support. It has 2 reactions in the x direction, y direction. A roller support has only 1 reaction. And this is an interesting kind of support that you may not have seen in it before. See, if it is a this kind of roller, if it is a basically it has, if there are three rollers given here in most roller representation you will see two roller wheels. So that means it will only give one reaction perpendicular to the plane, to its plane of placement. Here if there are three or more wheels, then the moment will also be restricted. You can imagine that if there are two wheels, I mean if there are two wheels you're placing on a two connected wheels you're placing on a floor, you can rotate it, but if there are three wheels you actually cannot rotate it. So this kind of boundary condition provides you two reactions, not the same as hinge support. It provides a vertical restraint, and it also provides a moment restraint. So the total number of external reactions is 3 plus 2 plus 2 plus 1, and that is 8. So we have 8 external reactions, and we know that equations of equilibrium is always 3. So 5 is a degree of external indeterminacy. And the number of members is 1 2 3 4 5 6 7 8 9 10 11 12 13 14. And the number of joints is 1 2 3 4 5 6 7 8 9 10 11 12. So in this formula, 3 into 14 plus 8 minus 3 into 12 minus 0, because there are no releases, there are no internal hinges, and that is equal to 14. And we know that we calculated that the degree of external indeterminacy was 5. So the degree of internal indeterminacy is 14 minus 5, that is 9. So this is how we calculate the degree of indeterminacy of frames. So once again, like the way we do for beams or trusses, the moment you are given a frame to solve, the first thing you do is calculate its degree of indeterminacy, both external and internal. So if it is a determinate frame, you can easily solve it. If there is some degree of indeterminacy, there will be some complications. I mean, you will have to employ some other methods, a force method or a displacement methods. And the force method is what we will look at today. This we have already looked at, so I'll only briefly go through it. For force or the two approaches to solve indeterminate structures are the force methods and the displacement method. So the force approach is also known as the compatibility or the flexibility method. And redundant forces, here the redundant forces are chosen as unknowns, and additional equations are obtained by considering the geometric conditions imposed on the deformations of the structure. These are the compatibility condition. What does this mean? Basically, redundant forces are, we have the number of redundant forces equal to to the degree of static indeterminacy. So for example, in maybe in this example, there is this is 1 degree externally indeterminate. So this prop reaction, support, even if this prop reaction did not exist, if this was only a fixed beam, even then the structure will be determinate and stable. So this force we can take as a redundant force. Redundant means that even if you remove that force, the structure will retain its stability. But if but from a cantilever beam, if you remove one of the restraints, if you remove the moment restraint, you will see that the structure will collapse. So that is not a stable structure. So in here you can up to three forces you can remove and the structure will still remain stable. For example, if you remove the x direction force, y direction force, and moment all from D, you make D a free point. Even then the structure will be stable because there will still be three equations, three constraints here. So there will be one redundant force corresponding to each degree of indeterminacy. So there's those that is a redundant forces. So the redundant forces are chosen as unknowns. So we have, so if the degree of static indeterminacy is 5, we will have 5 unknowns, and we need 5 additional equations. Additional, what does this additional word mean? It means that the equations of equilibrium we already have, but we need 5 additional equations to solve, and those are solved by obtain by considering the geometric conditions imposed on the deformation of a structure. They are called as compatibility conditions. There are several There are several methods for implementing the force method: the method of consistent deformation, the virtual work or unit load method, strain energy method, method of minimum potential energy, and flexibility matrix method. Here we mainly look at only the method of consistent deformation for all three of beams, trusses, and frames. And the displacement and equilibrium or stiffness method, they follow a different approach. There the displacement of joints are taken as unknown, and equilibrium equations are expressed in terms of these displacements and internal loads. These equations are solved to give actual joint displacement from which the redundant forces can be calculated. What we do here is we solve the redundant forces using the compatibility conditions, then we end up with a determinate structure which we can solve fully to solve the support reactions, to solve the internal displacements and everything. Here we do the reverse. We are the displacements are solved first, and then we support. Then we get a determinate structure from where we solve the redundant forces and the support reactions. And here there are three methods: moment distribution, slope deflection, and stiffness matrix method. Actually this approach is more commonly used. So all three of these methods are very important for this course and for your future also if you plan to pursue civil engineering. So the next 3 weeks, week 10, 11, and 12, are each dedicated to one of these methods. I think next week is slope deflection, week 11 is moment distribution, and week 12 will be the stiffness matrix method. The difference between the two methods, as I said, in the force method, unknowns are taken as internal member forces or reactions, the redundant ones, obviously the additional ones that we don't need for stability. And displacement method, unknowns are taken as joint displacements. Here in force method, to find the unknowns, compatibility conditions are written, which we have been doing so far for beams and trusses. Today we will do that for frames. And in displacement methods, to find the unknowns, joint equilibrium conditions are written, which we will look at from next week onwards. Here in the force method, the number of equations needed is equal to the degree of static indeterminacy, which we have studied in detail so far. In the next class, we have to look at the degree of kinematic indeterminacy. In the displacement methods, the number of equations needed is not equal to the degree of static indeterminacy. Basically, static indeterminacy is easier to perceive. We can perceive it, but kinematic indeterminacy will take some time getting used to. And in displacement methods, the number of equations needed is the degree of kinematic indeterminacy, and these two need not be equal, or they don't stand for the same thing at all. So obviously, if ds, degree of static indeterminacy, is less than degree of kinematic indeterminacy, the force method is suitable because the number of unknowns is equal to the number of degree of static indeterminacy, ds. So we would of course prefer to solve lesser number of unknowns. So this method is suitable when ds is less than dk, and this method is suitable when ds is greater than dk, which we'll look at next week. Now we move on to an example of analysis of indeterminate frame by method of consistent deformation. First example, uh, we want to this is first let us see if this is an indeterminate frame or not. This is a frame with two members. There is a hinge support and another hinge support. So there are basically four support reactions in here, in ra in the horizontal direction, ra in the vertical direction, rb in the horizontal and vertical direction each. So we have four external unknowns and we have three equations of equilibrium. So it is externally 1 degree indeterminate, and internally it won't be indeterminate. We can find that by using that formula that we use. There are two members, so m is 2 and the number of joints is 3. So if we apply that formula, 3m plus re minus 3j, we will find that is equal to 1. So the degree of indeterminacy here is 1, and that is an external degree of indeterminacy. So we need to determine the support reactions in this frame. So by the principle of superposition. What we have been doing even for beams and frames, for beams and trusses, what did we do? We chose one redundant force, or as many redundant forces as we have indeterminacy, and we would remove that flow force from that, remove all the redundance from the frame and from the structure, and we would make it a determinate structure. A determinate structure we can solve, and by the principle of superposition we will superimpose that in the primary structure will be just the structure without all the redundance, and we will make an additional structure where there is none of these applied forces, where there is only a redundant force. A redundant force, like if you take RB in the vertical direction as a redundant force, there will be a unit load in that direction, in along the direction of RB in the vertical direction, and we will apply the compatibility condition that since there is a hinge support at point B, there can be no net vertical deflection. So the vertical deflection due to the primary structure and due to the other structure, they have to add up to zero. By, as we said, the frame is indeterminate to the first degree. For the principle of superposition, we will choose the horizontal reaction at support B as a redundant. Any of it you can choose. I mean, among the four total number of support reactions we have, we can choose any of them as redundant. So we choose the horizontal reaction as redundant. So the pin at B is replaced by a roller. I mean, you can represent it like that. That if there was only a roller support here, there would be no horizontal force at B. Since a roller will not constrain B in the horizontal direction, so this structure will deform in any way. I mean, the deformation pattern can be anything, but there will be some deflection here because there is no constraint here. So there is a delta B we get from here in the primary structure, that where we have removed the redundant force, we have some deflection delta B here. And this is the primary, see, the actual frame is the primary structure plus a redundant bx applied. It is like the bx, whatever we say, that the reaction force at B in the x direction is applied. We are assuming in this direction, it can be in any direction. I mean, you will get the sign accordingly. And where we didn't trusses, bx is the magnitude and small fbb is the displacement here due to a unit load applied here in the horizontal direction. So basically, by principle of linear superposition, if small fbb is the deflection here due to a unit load applied at B, then the total deflection here will be capital Bx into small fbb. And by the compatibility condition, what do we know? We know that though in the primary structure we have temporarily forgotten about the horizontal constraint, there is a horizontal constraint. So at B there can be no net horizontal deflection. So delta B plus Bx into FBB have to add up to zero. That is what we have basically been doing for beams and trusses as well. And in frames, it is just that the calculations are different, but the concept remains the same. So the compatibility equation we end up with is delta B equal to Bx plus FBB. And what approach do we follow? These are both determinate structures. The interesting thing, the important thing is that we divide the actual structure in a number of structures in such a way that each of them are individually determinate, because if they are indeterminate we will not be able to solve them either. So this is a determinate structure where we can solve the delta B. This is a determinate structure where we can solve the small f bb, that is due to a unit load applied at this point, and we can get the magnitude of bx as minus delta B by fbb. So the terms delta B and FBB will be computed using method of virtual work, which we have done earlier. I think in week 3 we did it. The frame's x coordinates and internal moments are shown in the figure here, and it is important that in each case the selected coordinate x1 or x2 is the same for both virtual and real loadings, and the positive directions of capital M and small m must be the same. Basically, small m represents the unit loaded structure and capital M represents the actual structure with the redundant force removed. So this is the primary structure and this is the unit load structure. For delta B, we require application of real loads and a virtual unit load at B. Here uh, this is a frame structure. Here we have the load that we had applied, and since we want the deflection here, we apply a unit load here. So, and here we basically, what we did in trusses, we did this as a sigma form, because in truss each member is discrete. So what we did basically was we took the primary structure, we took a unit loaded structure, and we multiplied the response and divided by ei and added it for each of the elements. In a frame, however, this is the formula we will use. capital M small m by EI, and with this we will integrate over the entire dx over 0 to L. And here of course, see, for this member and this member, the x are oriented in different direction. X has to be along the along the length of the frame element. So we will take it in two parts. In integration we can just add. Here we will take, for once we will take for 0, for x1 equal to 0 to this length is 5, so we will take from 0 to 5 when d for dx1, and then we will take from 0 to 4 as dx2. X2 you can take from this end or this end, but it has to be oriented along this line. Now let us study the moments. Here first we solve the support reactions. When we solve the support reaction, we will see that there will be no horizontal force here, because see, this horizontal support reaction is not here, okay, in the primary structure. So there can be no horizontal force at A, because who is there to balance it? And we have total 8 kilonewton per meter over 5 meters, so we have total 40 kilonewton downwards. And since this is loaded symmetrically with respect to RA and RB, that they provide a support reaction of 20 kilonewton each. So for when x1 goes from this point to this point, from A to this point C, we have a moment of 20 into x1 minus 8 x1 square by 2. This we have done for bending moment long back in the first week, I think. For beams, this is a frame element, because there could have been axial force, but here there is no axial force, so this is essentially acting like a beam element. So the total moment will be, if you come to this point, if you take a section x1 here, you can see that there will be moment due to two forces. One is this reaction, that is 20 into x1, and other is this distributed force. This is distributed over a length of x1, so the total force is 8 into x1, and this will act as at the centroid of the force. So we have to multiply it with x1 by 2, so we effectively get 4x1 square. This is the moment we have to, so this is m1, and the small m1 is basically the same structure. We keep the same boundary conditions, but we remove the actual loading, and we just provide a unit load here. So if we provide a unit load 1 kilonewton here, there has to be a 1 kilonewton at the support, and we can see by conserving moment we have three equations of equilibrium, right? One along the x direction, one along the y direction, and one moment. So if we solve the support reactions, we will find that there will be two forces here, zero point 0.8 upwards, zero point 0.8 kilonewton downwards. So this m small m1, if we take a section x1 here, this 1 kilonewton acts along the length. So the line of action is the same as the frame, so it will not provide any moment about this point. But the zero point 0.8 kilonewton will provide 0.8 x1. So let us see this part. This part is for this part, this A to C. We have 20x1 minus 4x1 square, that is capital M. Small m we have 0.8 x1 by EI, that we have to integrate from 0 to 5 dx1. Now we will look at this part of the, so don't be confused seeing this oriented like this. Normally beams are oriented in the horizontal plane, but it can be vertical as well. The concept does not change. So here we take a section x2. From here, this x2 will range from this point to this point. So here there is no moment, because the 20 kilonewton acts along the line of the frame, so there will be no moment about this point, and there is no horizontal force. So capital m2 is 0, so this term will be 0. This term is basically 0. Just for the sake of study, here we know that the small m2 is not 0, because there is a transverse loading here. This 0.8 kilonewton will have no contribution in moment, but the 1 kilonewton will give a 1 into x2. And the thing is, take the sign convention as same. I mean, if see, if here to this 20 kilonewton, this moment that 20 kilonewton is giving is in the clockwise sense. If the clockwise sense is positive for the capital M1, take the same for the capital M2. So 0.8 x1 is taken as positive. So this is what we get. This part is 0, and when we integrate it, we will get, this is a definite integral. So this will be basically be 20 into zero point 0.8, that is 16 x1 square minus 3.2 x1 cube, that we have to integrate. You know how to integrate. I mean, I hope you should know, you have studied these simple integrals in class 11 and 12. So we get this a value. We will get this as a numerical value, because this is a definite integral. Now for the compatibility equation, we have to find out the FBB, and this we will require application of a real unit load acting at B and a virtual unit load acting at B. See, these two, this case is not the same as this case. I mean, they turn out to be the same, but they are not actually the same. This was just to find out the displacement delta b of a determinate structure, and this we are doing to find out the fbb under unit loading. So for that, we have basically a unit load is applied at B, and whether a real unit load is applied at B or a virtual unit load is applied at B, we will end up with the same structure. So here we have this 8 kilonewton upwards, 1 kilonewton here. So x1 along this horizontal member, m1 will be 0.8 x1, and along this will be 1 into x1, because this 1 will contribute, this 0.8 will not. And here basically both the structures, the real loaded one and the virtual loaded one, have the same are under the same moment. So this is m square, basically 0 integral m square by ei. M square here is 0.8 x1 whole square, and we integrate it from 0 to 0 to 5. And this won't be 0, this is 1 x2 square, and this we integrate from 0 to 4. So adding this, we get 48 by ei. This is small fbb, that is the displacement at point b due to virtual loading, due to a real load of 1 kilonewton. And the compatible equation was 0 equal to delta b plus bx fbb. So we substitute the numerical values of delta b and fbb. So we will get bx as minus 3.47 kilonewton. What does that mean? That means that, what does the minus mean? Basically, we had assumed the bx to be in this direction. I mean, you have to remember that. So since it came out to be minus 3.47, it means that the bx is here in this direction, towards the left. And now that you have solved this was 1 degree indeterminate, you have solved one redundant force externally, one redundant external force. So now you have a you have a determinate structure in your hand. This structure has now become this in this structure. Basically, now the unknowns are ax, ay, and by, because bx you already know, so you can just treat it as an applied force in bx, in the x direction at b. So you can solve them by using the three equations of equilibrium. You can solve the support reactions, then you can solve the entire displacement profile of the actual structure. Don't confuse with this. Primary structure is not the actual structure. So the displacements you have found here is not that of the actual structure. For finding out the displacement or the bending moment and shear force diagram of the actual structure, you have to apply the bxx that we found here, and then you have to solve this determinate structure step by step. As you saw, that first solve the support reactions, then you can find the bending moment shear force diagrams, you can find out the displacement using the virtual work method, and so on. So this was an example of how to solve a frame. This is another example. So here we will determine the moment at the fixed support A for the frame shown. So this is a roller, okay. This is a roller. It will give one force in the direction perpendicular to its surface, and this is a fixed support, so it will give three reactions. So externally it has four total reactions and three equations. So it is single degree indeterminate, and external force is there is one external redundant force. You can take that as any of the forces. You can take this horizontal force, you can take this vertical force, you can take this moment, you can take this reaction force. But if you are asked to determine the moment at the fixed support A, of course you will take ma as your redundant force, because because the redundant force is the first thing you will solve. So we will take ma as if we take ma as a redundant force in the primary structure, this will become a hinge support effectively, because it will give restraints in the x and y direction, but not a moment support. So this frame is indeterminate to the first degree. By principle of superposition, ma can be directly obtained by choosing as the redundant. The capacity of the frame to support a moment at A is removed, and therefore a pin is used at A for support, as I said. So this is the primary structure. It has a pin support here and a roller support here. Now my compatibility is about the rotation. Okay, earlier we were concerned about displacement, because we took a force as a redundant. If you take a moment as a redundant, you will get an unknown moment. So basically in this primary structure at this A, moment is not restrained. a hinge support is free to rotate, right? So this A will undergo some rotation theta A. So in this primary structure, this theta A is what we need to find out, and from this and the other the, where the only the redundant MA is applied, what will happen? We will remove this force, this applied force we will remove. The boundary conditions will remain the same. So at this point, we will apply a force, moment MA, and alpha AA is the moment at A due to a unit moment applied at A, just like we did earlier. So theta, but since this is fixed, there can actually be no net rotation at this point A. So the compatibility condition is theta A plus MA alpha AA equal to 0. Here theta A you can solve because this is a determinate structure with all the loading and boundary conditions known. Alpha AA you can solve because this is basically just a frame with a unit moment applied and no other force. And the boundary conditions also, one hinge here, one roller here. So theta A and alpha AA we will solve with using the principle of virtual work. And MA is what is the unknown, because MA is the moment that you need to impose this compatibility equation, and the terms theta and alpha A will be computed using the method of virtual work, and the frame's x coordinate and internal moments are shown. Like, we will take, see, always take the x1 and x2 along the length of the frame. Even if it is an inclined member, you take the x1 or x2 simply along the length. So here there are two members, and for the primary structure, to find out the rotation here, what do we have to do? We have to, uh, first we have to take the normal structure, then we have to apply a unit moment at this point, and we have to calculate, and we have to find out the moments along this. So for, if you solve the support reactions, see, basically this roller support, even if the member is inclined, the roller support always provides a force perpendicular to its plane. So here it is, the roller is resting along a vertical plane, so it will, the net force it will provide is along the horizontal direction. Now it will have two components, along the frame element and perpendicular to the frame element. So solving that, since this is a determinate structure, you can solve this using equations of equilibrium. This is what you get. 370.8 is the net reaction. So along the frame member we have 225, and perpendicular to the frame we have 296. This you just can find out using the angle, like you know the angle. Here if you know the member lengths, this is 5 feet, this is 4 feet, this is 3 feet. So you know the cos, sine, and tan theta. Once you have solved the support reactions, if you first we will take x1 from this point to this point. So x1, so we need the expression of moment in terms of x1. This 300 will not contribute. 29.17 into x1 is the moment here, because there is no distributed loading. And along this here we take x2 along this, from this point to this point. So for here you will see that due to this two, see, this 370, you split into these two components. Always, if there is a force on a frame member that is not along its length or perpendicular to its length, split it into two components. One is its actual component, one is its shear component. So here the 220.5 is along the length of the frame member, so it is the actual component, and 296 is the perpendicular component. So 296 will provide the moment, 296.7 into x2. And here there is an applied, basically there is an applied force here, an applied uniformly distributed force. So 100 into, like we know, 100 into this part will be 100 into x2 into x2 by 2, because this will act effectively on the centroid of the applied force. So they are in opposite senses, because this 2 to 296 gives in this sense, and this 4 gives in this sense, so they are subtracted. And remember the sense, since you are taking 296.7 that moment as positive, so you're basically taking the anti-clockwise moment here as positive, so this we will take as negative. And even for this unit load part, you have to take the same sense. You have to take here, you have to take the anti-clockwise as positive and the clockwise is negative. So m1 and m2 expressions we have got. Now for this, to find out this theta at A, we need a structure where the boundary conditions remain the same, and we provide just a unit moment at this point. One, see, here we are working with pound and feet. LV is pound and feet. Most often we work in kilonewton millimeter. Just be consistent about the units everywhere. So here, solving the support reactions in the same way, here we m1 we get as this one remains constant. This one moment, since this is an applied moment, that will of course be in the expression of m1, and due to this force, this horizon, this transverse force 0.0833, we get another moment, that is from here we find out the m1, and the m2 we find out this in the same way. We split this reaction force into two, the axial and the shear components, and only the shear component can provide a bending moment. So for theta A, we require application of real loads and a virtual unit couple moment at A. This is the real one, this is the virtual one. And like we work here for each length of for the each member, we will take one integral here. This length is 8, so from 0, as x1 varies from 0 to 8, we will integrate capital M1 into small m1 dx1 by ei, and this length is 5, so we will integrate capital M2 small m2 by ei dx2 from 0 to 5. These are both definite integrals, and so you will end up with a numerical value. Ei is I mean, if it's not provided, you keep ei as ei, but technically you are supposed to know that. And for alpha A, what will we do? We will just apply a unit, a real and a virtual unit moment here, just like we did. And they end up with giving the same structure. So we just need a small mx m1 and a small m2, and we have to multiply square them basically. So this is this 1 minus 0.0833 x1 whole square. We integrate this from 0 to 8, and this 0.0067 x2 whole square we integrate from 0 to 5, and if we add these two, we will get another numerical value. And substituting these results into the compatibility condition that we found earlier, because there can be no net rotation at the point A since it is a fixed support, we get that 821.8 by ei plus ma into alpha aa, that is 4.04 by ei. The ei gets cancelled anyway, so you don't have to substitute the values even if you know that. And ma we get as minus 204 pound feet. The negative sign ma indicates that ma acts in the opposite direction to that shown in the figure. What we assumed ma to be, it acts in actually the opposite sense. So the I mean, if you know this concept, you can solve any frame. You can be given more complicated frames. You can be given a frame with three members, in which case in this integral you have to add three terms. You have to integrate from, for each member you will take a dx1 dx2 dx3 that ranges from one end of the member to another end. So there will be summation of that many number of integrals. So mostly I guess you will be given two member frames, because these are calculation intensive jobs. You have to solve so many integrals, so and you have to then put the definite values and all. So these are the common types of frame problems you can be expected to encounter. So if there are any questions. Okay, if there are no questions, this is, I will just give a brief preview of what we are going to study next week. We will study the slope deflection method, which is a displacement method, and we will start with finding out the degree of kinematic indeterminacy which we have not looked at so far. Once we know the degree of kinematic indeterminacy, that will be equal to the number of unknowns, the number of unknown joint reactions, joint equations, joint unknowns. So we will solve them using the slope deflection method, and from there, from once we know the unknown joint displacement, we can solve the unknown forces, and we can solve the entire structure the way we did here with the forces. There we will do with the displacements. So next class we will, for week 10, we will start with the degree of kinematic indeterminacy and the slope deflection method. Okay, then if there are no questions, I will end the class. See you next week.